Welcome! In today's session, we'll be diving into LeetCode problem number 801, minimum swaps to make sequences increasing. This is an interesting dynamic programming problem that challenges us to transform two sequences into strictly increasing ones with the minimum number of swaps. Let's explore the problem, break it down, and uncover the most efficient solution. Let's get started. In this problem, we are working with two integer arrays, nums1 and nums2, which are of the same length n. These two arrays represent sequences that are initially unsorted, and our goal is to make both sequences strictly increasing. For nums1, this means that each element must be smaller than the one that follows it, and the same applies to nums2. To achieve this, we are allowed to swap the elements at the same index between the two arrays. For example, if we swap at index I, the values nums1, I, and nums2, I, are exchanged. Each swap counts as one operation, and we need to determine the minimum number of swaps required to make both sequences strictly increasing. If it turns out to be impossible to achieve this, the function should return -1. The input consists of the two integer arrays, and the output is the minimum number of swaps needed or -1 if it cannot be done. Let's look at an example to understand this better. Suppose nums1 is 1, 3, 5, 4, and nums2 is 1, 2, 3, 7. In this case, the output is 1. Why is that? Well, the only swap required occurs at index 3. When we swap the values at this index, nums1 becomes 1, 3, 5, 7, and nums2 becomes 1, 2, 3, 4. After this single swap, both sequences are strictly increasing. Notice how each element in nums1 and nums2 is now greater than the one before it. This demonstrates that just one swap is sufficient to achieve the desired result. Here's another example to consider. This time, nums1 is 0, 3, 5, 8, 9, and nums2 is 2, 1, 4, 6, 9. The output in this case is also 1. The swap happens at index 1. After the swap, nums1 becomes 0, 1, 5, 8, 9, and nums2 becomes 2, 3, 4, 6, 9. Now, both sequences are strictly increasing. This highlights how we might need to swap strategically at only specific indices to minimize the total number of swaps. In our third example, nums1 is 1, 5, 6, 7, and nums2 is 1, 3, 4, 6. Here, the output is 0. That's because both sequences are already strictly increasing, so no swaps are needed. This is a straightforward case where we simply observe that the input already satisfies the desired condition. Additionally, the problem includes some important constraints. For instance, the length of nums1 and nums2 can go up to 10⁻⁴, and the values in these arrays can range from 0 to 2 *10⁻⁵. These constraints mean that our solution needs to be efficient and capable of handling large inputs. Finally, we need to consider edge cases. For example, if it's impossible to make both sequences strictly increasing, the function should return -1. This might happen if the values in the arrays are such that no sequence of swaps can achieve the desired condition. Additionally, since the input size can be very large, our solution must be optimized to run efficiently within the given constraints. This ensures that it works correctly for all valid inputs, including edge cases and large-scale scenarios. To tackle the problem of making two sequences strictly increasing with the minimum number of swaps, we can consider a few approaches. First, the brute force approach involves generating all possible combinations of swaps and non-swaps at each index, while ensuring the sequences remain strictly increasing. This approach essentially explores every possible path and calculates the total swaps required for each. However, the key limitation here is its exponential time complexity of O2 to the power of n, since for every index, there are two choices, to swap or not to swap. While this approach is conceptually straightforward, it quickly becomes computationally infeasible for larger input sizes, such as when n equals 10,000. As an alternative, dynamic programming offers a more structured and efficient method. By defining two states, keep I and swap I, we can track the minimum swaps required to maintain an increasing sequence either without swapping or with swapping at the current index. This allows us to systematically build the solution by inheriting or transitioning between states based on the values and relationships of the elements in the sequences. Now, when swapping becomes necessary to maintain the increasing order, the transitions between the keep and swap states must be handled carefully. For example, if we decide to keep the current index unchanged, we may inherit from the swap state of the previous index. As a swap, there could ensure the sequences remain valid. Similarly, if we choose to swap at the current index, we would add 1 to the keep state of the previous index, since that state required no swap. This dynamic programming approach allows us to iterate through the arrays just once, achieving an efficient time complexity of O(n). Initially, the space complexity is O(n) due to the storage of the keep and swap arrays. However, this can be optimized further by recognizing that the states at index I depend only on the states at index I1. By reusing just two variables, prev_keep and prev_swap, we can reduce the space complexity to O(1). This optimization maintains the same runtime efficiency while significantly reducing memory usage, making the algorithm highly scalable. Given these considerations, the optimized dynamic programming approach emerges as the best strategy for this problem. It combines linear time complexity with constant space usage, leveraging the insight that the solution only requires tracking two states, keep and swap, that depend on the previous index. This eliminates both the exponential computations of the brute force method and the unnecessary memory overhead of full DP arrays. While the brute force approach is easier to conceptualize, its computational inefficiency makes it impractical. On the other hand, the space-optimized dynamic programming method not only solves the problem efficiently but also handles large constraints, such as n up to 10,000, with ease. In summary, this approach strikes the perfect balance between simplicity, efficiency, and scalability, making it the ideal solution for achieving the minimum swaps required to make the sequences strictly increasing. We are tasked with determining the minimum number of swaps required to make two integer sequences, nums1 and nums2, strictly increasing. A swap involves exchanging the elements at the same index between the two sequences. Importantly, both sequences have the same length, and our goal is to ensure that, after the swaps, both sequences are strictly increasing across all indices. To solve this problem efficiently, we use a dynamic programming approach to track the state of the sequences. The first step is to define this state. Specifically, we use two variables, keep I and swap I. The variable keep I represents the minimum number of swaps needed to make the sequences strictly increasing up to index I without swapping the elements at index I, while swap I represents the minimum number of swaps needed when the elements at index I are swapped. This setup allows us to track both scenarios efficiently as we process the sequences. To begin, we initialize the states for the first index. Since no elements exist before index 0, no swaps are needed to make the sequences increasing at this point. Therefore, keep 0 is set to 0, representing no swaps if we do not swap the first pair, and swap 0 is set to 1, representing one swap if we do. Next, we iterate through the sequences from index 1 to n1, where n is the length of the sequences, to compute keep I and swap I for each index. This computation depends on two primary conditions. The first condition considers the case where no swap is performed at either the current index I or the previous index I1. If nums1 I is greater than nums1 I1 and nums2 I is greater than nums2 I1, then the sequences remain strictly increasing without a swap. In this case, keep I simply inherits the value of keep I1, while swap I becomes swap I1 plus 1 because swapping it I would require adding one swap to the previous state. The second condition considers the case where a swap is performed at index I but not at index I1. Here, if nums1 I is greater than nums2 I1 and nums2 I is greater than nums1 I1, we calculate keep I as the minimum of its current value and swap I1 and swap I as the minimum of its current value and keep I1 plus 1. These conditions ensure that our transitions maintain the strictly increasing property. After iterating through all indices, the final result is determined by taking the minimum of keep n1 and swap n1. This gives us the minimum number of swaps required to make both sequences strictly increasing. Key insights from this approach include the use of dynamic state transitions. By examining the two conditions for each index, we ensure that only valid transitions where the sequences remain strictly increasing are considered. Additionally, we can optimize the space complexity of this solution by reducing the storage requirement. Instead of using arrays for keep and swap, we only store values for the current index and the previous index, reducing the space complexity from O(n) to O(1). Finally, it's important to handle edge cases, such as when no swaps are needed because the sequences are already strictly increasing, when every index requires a swap, or when some indices require swaps while others do not. These considerations make the solution robust and efficient. The time complexity of this algorithm is O(n), as we iterate through the sequences once, processing each index in constant time. The space complexity, after optimization, is O(1), because we only store the current and previous states instead of maintaining full arrays for keep and swap. To illustrate how the algorithm works, let's walk through an example. Suppose nums1 is 1, 3, 5, 4, and nums2 is 1, 2, 3, 7. First, we initialize the states, keep 0 is 0 and swap 0 is 1. At index 1, nums1, 1 is 3, and nums2, 1 is 2. Both conditions are satisfied, so keep 1 remains 0 and swap 1 becomes 2. Moving to index 2, nums1, 2 is 5, and nums2, 2 is 3. Again, both sequences remain strictly increasing, so keep 2 stays 0 and swap 2 is updated to 3. Finally, at index 3, nums1, 3 is 4, and nums2, 3 is 7. At index 3, nums1, 3, and nums2, 3 require careful consideration. By evaluating the conditions, we find that keep 3 becomes 1, indicating that one swap is needed to maintain the strictly increasing property without swapping at index 3. Similarly, swap 3 becomes 2, accounting for the scenario where a swap is performed at this index. The final result is the minimum of keep 3 and swap 3, which is 1. This means only one swap is needed to make both sequences strictly increasing. To optimize further, we can replace the keep and swap arrays with two variables to save space. Additionally, early termination can be employed if a valid solution is identified before reaching the last index. These optimizations ensure the solution is both time efficient and space efficient while maintaining accuracy in a variety of scenarios. This implementation solves the problem of finding the minimum swaps needed to make two sequences strictly increasing. The approach uses dynamic programming with two arrays, keep and swap. Keep I tracks the minimum swaps needed if no swap occurs at index I, while swap I tracks the swaps if a swap happens at index I. Initially, at index 0, no swap keep 0 is 0 since no swaps are necessary, and swapping at the start, swap 0, is 1 because it requires one swap. Then, iterating over the indices from 1 to n1, we check two conditions. 1. If both sequences are already increasing without a swap at I, we update keep I to keep I1, since no additional swaps are needed, and swap I becomes swap I1 plus 1 to reflect a swap at the current index. 2. If the sequences can be increasing with a swap at index I, we update keep I to the minimum of its current value and swap I1, meaning a swap at I1 can lead to no swap at I. Similarly, swap I is updated to the minimum of its current value and keep I1 plus 1, meaning no swap at I1 but a swap at I. Finally, the result is the minimum of keep-1 and swap-1, representing the minimum swaps needed for the entire sequence. This approach ensures correctness while maintaining an O(n) time complexity with O(n) space, making it efficient for large inputs. Here, we start implementing the solution to find the minimum number of swaps needed to make both sequences strictly increasing. We define two arrays, keep and swap, each of size n, where n is the length of the input arrays. Keep I represents the minimum swaps required if we do not swap the elements at index I, while swap I represents the minimum swaps required if we do swap the elements at index I. Initially, both arrays are filled with a maximum value to signify that no computations have been performed yet. At the very beginning, if we do not swap the first elements, the cost is 0, so keep 0 is set to 0. If we decide to swap the first elements, swap 0 is set to 1. Next, we iterate through the arrays, starting from index 1. We handle two main cases. First, when both sequences remain strictly increasing without a swap at index I, the values of keep I and swap I are updated based on the previous values of keep I1 and swap I1. Specifically, keep I simply takes the value of keep I1 and swap I takes the value of swap I1 plus 1 because a swap at the current index increments the total swap count. Then, we move on to the next condition. The second condition occurs when both sequences become strictly increasing only after swapping the elements at index I. In this case, we update keep I to be the minimum of its current value and swap I1, since swapping the previous index might lead to fewer swaps overall. Similarly, swap I is updated to be the minimum of its current value and keep I1 plus 1, as we would need to add one more swap for the current index. After we have processed all indices, the result is simply the minimum value between keep n1 and swap n1, representing the least number of swaps required to make both sequences strictly increasing. Finally, we return this result to complete the function implementation. Here, we're tackling the problem with our first example, nums1 equals 1, 3, 5, 4, and nums2 equals 1, 2, 3, 7. First, we initialize our variables. The length of the arrays, n, is 4. We then set up two arrays, keep and swap. The keep array tracks the minimum swaps needed if we do not swap the numbers at a given index, while swap tracks the swaps if we do. Initially, keep is set to 0, infinity, 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 meaning no swaps are needed at the start if we don't swap, and swap is 1, infinity, 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 because swapping the first pair costs exactly one swap. At step I equals 1, we evaluate two conditions. First, both nums1, 0, is less than nums1, 1, and nums2, 0, is less than nums2, 1. This means we can maintain the increasing order without a swap, so we set keep 1 equal to keep 0, which is 0. To account for swapping, we add 1 to swap 0, resulting in swap 1 being 2. Next, we check if nums1, 0, is less than nums2, 1, and nums2, 0, is less than nums1, 1. This condition allows us to transition between the two arrays. Here, we update keep 1 to the minimum of keep 1 and swap 0, which remains 0, and swap 1 to the minimum of swap 1 and keep 0 plus 1, resulting in 1. At this point, the state arrays are keep equals 0, 0, infinity, infinity, and swap equals 1, 1, infinity, infinity. Moving to step I equals 2, we again evaluate conditions. If nums1, 1, is less than nums1, 2, and nums2, 1, is less than nums2, 2, we update keep 2 to keep 1, which is 0, and swap 2 to swap 1 plus 1, resulting in 2. Similarly, for the transition condition between arrays, we set keep 2 to the minimum of keep 2 and swap 1, which remains 0. Next, we update swap 2 to the minimum of swap 2 and keep 1 plus 1, resulting in 1. At this point, the state arrays are keep equals 0, 0, 0, infinity, and swap equals 1, 1, 1, infinity. Now, in step I equals 3, the first condition, nums1, 2, less than nums1, 3, and nums2, 2, less than nums2, 3, does not hold. However, the second condition, nums1, 2, less than nums2, 3, and nums2, 2, less than nums1, 3, does hold. This means we can only achieve the desired order by transitioning between the arrays. For this, we set keep 3 to the minimum of keep 3 and swap 2, which is 1, and swap 3 to the minimum of swap 3 and keep 2 plus 1, resulting in 2. The final state arrays are keep equals 0, 0, 0, 1, and swap equals 1, 1, 1, 2. To determine the result, we take the minimum of keep 3 and swap 3, which is 1. This tells us the minimum swaps required to make the sequences increasing for this example is 1. Now, we begin another example with nums1 equals 0, 3, 8, 9, and nums2 equals 1, 4, 6, 10. First, we initialize. Here, n is still 4, and the keep array starts as 0, infinity, 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 while the swap array is 1, infinity, infinity, infinity. At step I equals 1, we evaluate the conditions. If nums1, 0, is less than nums1, 1, and nums2, 0, is less than nums2, 1, we set keep 1 equal to keep 0, which is 0, and swap 1 to swap 0 plus 1, resulting in 2. For the transition condition, nums1, 0, less than nums2, 1, and nums2, 0, less than nums1, 1, keep 1, is updated to the minimum of keep 1 and swap 0, which remains 0, and swap 1 becomes the minimum of swap 1 and keep 0 plus 1, resulting in 1. At this stage, the state arrays are keep equals 0, 0, infinity, infinity, and swap equals 1, 1, infinity, infinity. Moving to I equals 2, nums 1, 1, less than nums 1, 2, and nums 2, 1, less than nums 2, 2, holds, so keep 2 is set to keep 1, which is 0, and swap 2 is swap 1 plus 1, resulting in 2. The transition condition also holds, so we update keep 2 to the minimum of keep 2, and swap 1, which remains 0, and swap 2 to the minimum of swap 2, and keep 1 plus 1, resulting in 1. The state arrays are now keep equals 0, 0, 0, infinity, and swap equals 1, 1, 1, infinity. At step I equals 3, nums 1, 2, less than nums 1, 3, and nums 2, 2, less than nums 2, 3, holds true, so we set keep 3 to keep 2, which is 0, and swap 3 to swap 2 plus 1, resulting in 2. The final state arrays are keep equals 0, 0, 0, 0, and swap equals 1, 1, 1, 2. The result, minimum of keep 3 and swap 3 is 0, indicating no swaps are needed to make the sequences increasing. In our final example, nums 1 equals 1, 2, 3, 7, and nums 2 equals 1, 2, 4, 6. We begin by initializing. Here, n equals 4, keep starts as 0, infinity, 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 and swap starts as 1, infinity, infinity, infinity. At step I equals 1, nums 1, 0, less than nums 1, 1, and nums 2, 0, less than nums 2, 1, holds, so keep 1 is set to keep 0, which is 0, and swap 1 becomes swap 0 plus 1, resulting in 2. The state arrays at this point are keep equals 0, 0, infinity, infinity, and swap equals 1, 1, infinity, infinity. At step I equals 2, both nums 1, 1, less than nums 1, 2, and nums 2, 1, less than nums 2, 2, hold, so we set keep 2 to keep 1, which is 0, and swap 2 to swap 1 plus 1, resulting in 2. The state arrays are now keep equals 0, 0, 0, infinity, and swap equals 1, 1, 1, infinity. At step I equals 3, nums 1, 2, less than nums 1, 3, and nums 2, 2, less than nums 2, 3, holds, so keep 3 is set to keep 2, which is 0, and swap 3 becomes swap 2 plus 1, resulting in 2. The final state arrays are keep equals 0, 0, 0, 0, and swap equals 1, 1, 1, 2. The result is the minimum of keep 3 and swap 3, which is 0. This means no swaps are needed to make the sequences increasing in this example. The time complexity of this algorithm is determined by the single iteration through the input arrays, nums 1 and nums 2. For every index from 1 to n1, the algorithm evaluates two conditions to decide if the sequences remain increasing without a swap or if a swap is required to maintain the order. This evaluation involves a few constant time operations, such as comparisons and updates to the keep and swap arrays using the min function. Since these operations are performed for each index exactly once, the total number of operations is proportional to the size of the input, n. Mathematically, the loop iterates n1 times, and each iteration executes a fixed amount of work, resulting in a time complexity of O(n). This linear scaling ensures the algorithm is efficient even for large input sizes. Next, let's examine the space complexity. The algorithm uses two auxiliary arrays, keep and swap, each of size n, to store intermediate results during the computation. These arrays account for O(n) space usage. In addition, the algorithm employs a few variables, such as n for the length of the input, the loop variable I, and others, which require constant space, or O(1). It's important to note that the input arrays, nums 1 and nums 2, are not considered additional space since they are part of the given input. When we sum up the memory usage, the total space complexity is dominated by the O(n) space required for the keep and swap arrays. Therefore, the overall space complexity of the algorithm is O(n). To better understand the efficiency of this approach, let's compare it to a brute force method. A naive approach would involve testing all possible combinations of swaps and no swaps at every index, resulting in an exponential number of possibilities. Specifically, with n indices, there would be 2 to the power of n combinations to evaluate, leading to an infeasible time complexity of O(2 to the power of n). In contrast, the dynamic programming solution avoids this exponential growth by breaking the problem into smaller subproblems. It computes each state using results from previous states, reducing the complexity to O(n) time an O(n) space. This optimization ensures that the algorithm performs consistently well, regardless of the input size. Whether the input is small or large, the time complexity remains O(n), as each index is processed exactly once, and the space complexity remains O(n), due to the fixed size auxiliary arrays. Finally, let's solidify the time and space complexity analysis with a mathematical proof. The dominant operation in the algorithm is the loop, which iterates linearly through the input arrays. Each iteration performs a constant amount of work, such as comparisons and updates, which do not depend on the size of the input. This means the total work done scales directly with the input size, confirming a time complexity of O(n). Similarly, the memory usage is dominated by the keep and swap arrays, each of size n, while additional variables require only constant space. Whether the input is best case, average case, or worst case, these complexities remain the same. Thus, the algorithm's time complexity is conclusively O(n), and its space complexity is O(n) as well. One of the most common mistakes in this problem is overlooking the strictly increasing condition. Both sequences, nums1 and nums2, must remain strictly increasing after every operation. This means for any index I, the elements must satisfy nums1, I1, nums1, I, and nums2, I1, nums2, I. Skipping this validation often leads to incorrect solutions. Another frequent error is swapping elements without properly validating the outcome. A swap might disrupt the increasing order in one or both sequences, so it's crucial to carefully evaluate the result of a swap before making it. Dynamic programming, which is central to solving this problem efficiently, also introduces potential pitfalls. Initializing the DP arrays incorrectly, such as using infinity instead of valid base cases, can result in invalid results. Additionally, edge cases like single-element arrays or sequences that are already strictly increasing are often overlooked during testing. For example, if no swaps are required, the algorithm should correctly return 0. Finally, brute force solutions can be tempting but are highly inefficient for larger inputs. Since the problem size can go up to 10,000, a brute force approach with exponential time complexity will almost certainly lead to time limit exceeded errors, making a dynamic programming approach essential. This problem is a great way to showcase your problem-solving approach in interviews. Recognizing that this is a variation of the two-sequence alignment problem is an excellent starting point. The key insight here is using dynamic programming to track two states, one for when you choose to swap at a particular index and another for when you don't. Interviewers often look for how you refine your solution, so explaining how you transition from a brute force method to a dynamic programming approach with O(n) time complexity and eventually optimize for O(1) space is highly valuable. It's also important to emphasize your attention to detail by discussing specific edge cases, such as single-element arrays or sequences that are already sorted. These examples demonstrate that your solution is robust and well-tested. Additionally, you should be prepared to discuss trade-offs, like the benefits of reducing space complexity from O(n) to O(1) using iterative methods versus the simplicity of a more intuitive DP array approach. To deepen your understanding and impress your interviewer, you can also draw parallels to related problems, like Wiggle subsequence, which focuses on alternating sequences, or Russian doll envelopes, which uses sorting in dynamic programming. These connections show that you understand broader patterns in algorithmic problem solving. When exploring alternative approaches to this problem, a brute force solution might come to mind first. This involves checking all possible combinations of swaps, but with a complexity of O(2 to the power of n, it's impractical for larger inputs. A better approach is recursive dynamic programming with memoization, where you track the states of swapped and non-swapped sequences. This brings the complexity down to O(n), but requires O(n) space for the memo table. To achieve maximum efficiency, we can use an iterative dynamic programming approach with space optimization. Here, instead of maintaining full DP arrays, you keep track of only the previous state values, like prev_keep and prev_swap, reducing space complexity to O(1). The key insight is the state transition. At each index, you decide whether to swap or not based on the previous state and whether the constraints for nums1, I, and nums2, I, are satisfied. The initialization is straightforward. Start with keep set to 0, indicating no swaps at index 0, and swap set to 1, indicating one swap at index 0. From there, iterate through the sequences, updating these states based on the conditions. Finally, the result is simply the minimum of the keep and swap states at the last index. Great job! To wrap up, we reviewed the dynamic programming approach to solve minimum swaps to make sequences increasing. The key takeaway is leveraging state-based transitions for optimal solutions. Thanks for watching, and don't forget to like and subscribe for more insights on solving coding problems. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!